And we are recording. Hi, everybody. We're recording our second session here of Harmonic Experience for the summer of 2021. And we've got a small class today, but some people are going to be tuning in later and watching what's going on. We are going to www.Montoya's Great Music Theory Practice.weebly.com. And I gave that to you last week, so I'll say it again, www.Montoya's Great Music Theory Practice.weebly, weebly.com. And on the tab Harmonic Experience, you will find the paper that says, or the resource that says General Terminology. Find that one. That's what we're going to discuss right now. Okay, so I've made up this little distillation of what's going on inside the good book. Where's mine? Harmonic Experience, great book. You should have it if you don't already. And I've taken away the kinds of things that I think you should know and at least hear about, even if you don't understand it quite yet, before you get too deep into the book. Now, if you can, in the next week or two, go through chapters 1 through 5. Have you read much in this, Tom? You've already been reading, right? Art, if you've read anything in this, I'm going to be talking
Yeah.
about Art. There are only 2 in-persons today. But if you've gone through at least chapter 5, that's a good place to stop for a while and to really digest. They're not that long of chapters, and I listened to them. I think 1 through 5 I listened to on a 4 mile walk the other day. So within one walk, I had finished those 4 chapters. It's not, or those 5 chapters. It's not that long, but it takes us all the way up to the fifth partial, to hearing the major third, and it talks about a lot of these things that we're going to be talking about. But it gets you significantly into the theory if you understand perfect fifths and major thirds and how they're generated from the overtone series. So let's take a look at this little page here. Feel free to take notes on it or ask questions as we go. Please ask questions. And feel free to be uncomfortable with not knowing some of this stuff for a while. Just get some of these terms in your head, laying the groundwork. Okay, number one, the difference between just intonation and equal temperament. And so we were having a discussion before the class started, and we were talking about what equal temperament actually is and what just intonation is. So what is just intonation, and what have we gained by moving from a just system to an equal system over the history of our human music making? Just intonation refers to notes that are tuned to the low prime natural frequencies of the overtone series. That's a mouthful. And their reciprocals.
Dang.
What does all that mean? That's a lot, okay? And I showed this to Alaudin, and I took some of these definitions right out of his glossary, and he went through it with me and said, no, you should say it this way, you should say it that way. And he wanted to make sure that I was presenting it to people who are new to this way of thinking. He wanted to make sure that I was presenting it properly. So we went through this at length and in detail. And I wanted a little less wordy. Tunings that come out of the overtone series, but that left too much to be misinterpreted. So just intonation refers to the notes, the low prime natural frequencies, not all of the notes of the overtone series, just the low prime ones. What are the low prime numbers? Tom can tell us. What was your degree in, Tom?
Math.
It was
Operations research. Yeah.
math operations research. Okay.
3, 5, 7, 11. 2 is number 2.
Right. So Tom's giving us the primes, and we're really only going to focus on the lowest primes. One is a prime, not counted as prime. 2, 3, 5, and maybe 7.
7.
That's it, right? So we're not looking at all of the notes of the overtone series. We're looking at the lowest primes of that come out of the overtone series, which are 2, 3s, and 5s especially. Okay, so when we tune our notes, we're tuning to these low prime natural frequencies. Natural meaning they just appear because they're in the overtone series. And I like to tell the story that when the Big Bang first happened, and everything came into creation, all the laws of physics had become a thing right from that start, right? And everything was
Right.
going to follow those rules. Tell me if I'm crazy, Tom. But when everything starts, the natural laws of physics are giving us the overtone series from the very start of the universe, or even before that. Who knows? Maybe they were already in place before that, right?
Mhm.
But that means that the idea of overtones was already present, and I'm going to give you a really cool example of that in a little while. If anyone saw my Facebook post from last week, yes, I still use Facebook because I'm old. Okay, that's what the students in school tell me. Okay, now those natural low primes are the ones that give us our perfect fifths, our major thirds, and our octaves. That's really 90% of the book that we're going to be talking about. So last week when I kind of asked you guys if you could multiply by 2 or multiply by 5 or multiply by 3, and people thought I was setting them up for a trick, I was not. It's actually really all we're going to be dealing with for the most part, and certainly for this summer. Okay, so the reciprocals we'll get into. That'll make sense later. Now, what is equal temperament, and what did we stand to gain by getting rid of a just intonations system of tuning and use equal temperament? What did we stand to gain? Why do we have equal temperament? Anybody?
So we could perform musical pieces in every key.
Correct. You're both right. Art says in every key, and Tom says so we could modulate. Yes.
Mhm.
And as we learned how to modulate to closely related keys and then distant related keys and make all these kind of harmonic moves, that supported music that was interesting enough to listen to for 2 hours of a Mahler or Wagner piece, right? Or longer if it's an opera, because it was sustained by this harmonic interest. So the more harmonic choices we had, the more the music grew. So you go from a 25-minute Mozart symphony, to an hour-long Beethoven symphony, and an hour and a half to 2 hour Mahler symphony. So it just keeps growing until finally tonality just splits and breaks apart after Wagner, and it gets into the experimental stages and atonal music in the 20th century. So this is the development of our harmony here in the West, we call it. It just keeps growing and developing and changing and morphing, but it's based on all these ideas. So equal temperament, then let's look at that definition. Equal temperament is a system of tuning wherein the octave is divided into intervals of exactly the same size. So every half step is exactly equalized, which doesn't work with the regular tunings. And we learned last week that if we're going to sing an E, and then we play it on the piano in an octave, this E sounds higher than the E I was just singing. That E would be higher. And that we talked
Right.
about the fact that that is not that is not a sense, it's an actual pitch frequency difference. The string is vibrating differently than my vocal cords are vibrating because I am not using equal temperament. I'm using the just tuning of the overtone series of what we hear when we listen to one string. And when you hear that E, that's different. You can't probably hear it on Zoom, but that E is different than that E. Okay. In fact, it would be the same on the piano. Yeah, I did that wrong because I held down the E and I allowed it to ring.
Mhm.
But the E's are so out of tune on the piano that when we do it that way, we can hear it ringing. But when we do the G, it's closer. So we can hear that G really. Yeah.
Yeah.
The E disappears. But those notes, the G's and the E's, are already in that C note that I'm playing down below in the overtone series. So that's a little bit of review. Equal temperament doesn't use those ratios. It doesn't use those frequencies. It uses frequencies that have been equalized by stretching some notes sharp or flat in order to make every half step equal. Thus, equal temperament. Now, equal temperament doesn't have to be a 12-tone system. Equal temperament could be a 19-tone system. And I hear that there are systems where they tune to 19-tone equal temperament, in which case a cent would be, well, we haven't talked about cents yet, but cents are the divisions of each half step, 100 cents in a half step. But they would be a different size once you go to 19 notes, but you would need maybe 2 keyboards in order to do that. You couldn't play it on 1 keyboard. You'd have to stretch everything really different. The whole idea is once we get to the next C up, or the next fundamental up, once we do that octave, we have doubled the frequency of the original one. And so if that frequency is doubled, we get the next octave. We expand it, we double it again, that's another octave. Double it again, we get another octave. And every time we double the frequencies, we go up an octave in something we call octave expansion. We're expanding the octave by doubling its frequency. If this is 100, and this is 200, and this is 400, and this is 800, 1600, etc. Right? So doubling our octave frequencies is how we get the next octaves above that. Okay, so equal temperament then is a system of tuning where, and we're used to 12-tone equal temperament because that's what our piano does. And it divides each of those notes, those half steps, into all equal parts. And it allows us to play in any key we want to and to modulate to any key we want to. We don't have to stay in one key or closely related keys. We can start going all over the place. It's very easy to go from key of C to the key of F sharp really fast. And although it sounds a little wonky, we can get there if we want to because everything is equalized, right? If I wanted to get here. So we can move around very easily. Okay, so that's what we stand to gain. There's a problem with equal temperament though, and that is that it kind of dulls our senses a little bit to the resonances or the in-tuneness of just intonation. So we can get it. We can hear if it's justly tuned or not when the notes are close enough together. Like if we're singing in 4-part harmony, we're not more than a couple octaves apart, maybe 2-3 octaves apart or so. We can use those just tunings more than if we're using 8 octaves. It's a little tougher. So here's the analogy. The analogy is, yes, we can still get in tune to the just resonances, even though we play an equal temperament all the time. But we lost something. We lost that deep sensitivity to the overtone series and to those just tunings. And we just got to revive them in our mind a little bit. It's the same way the invention of the light bulb, which was a great thing for the human race, dulled our senses to the natural rhythms of day and night, right? We can stay up all night now if we want to, and we don't have to be by candlelight, and we can illuminate our cities so that it's so bright that you don't even know it's nighttime. So our senses get dulled to those natural rhythms of day and night and to the stars, just like we get our senses dulled to these natural resonances of the overtone series. It's all connected. All right, so there you go. That's number one. Any questions on that or anything else that you want to say or offer to that? Hold reciprocals in your pocket for a little bit and we'll get to those. Okay, number two. So the study that we're doing this summer is going to focus mainly on frequency ratios, mathematically quantifiable by the low prime numbers, 2, 3, and 5, and their various combinations. The ratio 2 to 1, which is a doubling, they're heard as octaves. Anytime you double something. If the original is 5, then the doubling will be 10, and then 20, and then 40, right? If the original is 3, then the next will be 6, and then it'll be 12 and 24, etc. The ratio 3 to 1, which is a tripling, is going to be heard as a perfect fifth. So thirds are fifths, kind of, as Tom said last week. The ratio 5 to 1 are going to be quintuplings, which are heard as major thirds. That's why we call them major thirds pentamerous. Okay. Now, harmony is generated by these low prime numbers first. Also, the way in which the numbers combine or compound, and the ear's receptivity to those ratios. Can your ear actually sense these ratios? Can you hear it? Can you experience it in the body? And if you can, then that's why this whole thing starts to make sense when we say, okay, when we're singing this on the board that we sang last week, and we said the two laws that are tied together sound different. Each one sounds different depending on the context, right? When your ear is receptive to that and your ear starts to latch onto that, then you're starting to make sense of this whole thing and what harmonic experience is all about.
I have a question on that, on our precepts on how we hear. How we hear is not exactly linear, and we're more sensitive to certain frequencies and stuff like that. I know that's a little bit different, but the sense, as far as sense go and tuning and stuff, I think isn't it not linear? I think we hear in either logarithmic or exponential. I think it's logarithmic, the way we hear, we perceive sound.
This is very good. And if you look down, peek ahead to number 5, we're going to talk about that a little bit.
Oh, okay.
In fact, now might be a good time to jump to it. So let's jump to it. Number 5, numerically, melody is additive. This is linear. I think it's getting to what you're asking. Maybe I'm wrong, but you're adding intervals and you're moving along a scale, right?
Right.
You
Right.
add certain amount of half steps, now you're up an interval, and that starts to become a melody as you move around, right? But harmony, so it's either additive or subtractive. But harmony is different. It's multiplicative. It has to do with ratios. Harmony is multiplicative, quantified by frequency ratios between the tones. So if I listen to 2 notes, I listen to a C and I listen to a D, let's go this C, and I listen to this D. What is the ratio between that note and that note? It has to do with multiplication rather than addition. And so the pairing of those 2 notes, and we hear them. So there's 2 separate ways of hearing. There's the melodic way and there's the harmonic way. The melodic way is easier because it's more about addition, and the harmony listening at the same time is different. I like this little paragraph in the book somewhere where Aladdin talks about you and your little teeny tiny self that is on your eardrum, and you're bouncing around because of all the rhythms that are being created on your eardrum, these ratios of the comparison of the 2 notes at the same time. And your ear is doing amazing things that we could never do with our motor muscle skills, right? We can tap a 3 to 1 ratio and feel that a 3 to 2 rather, or a 1 2 3 1 2 3 1 2. We can feel a 3 to 1, but once I start getting to, let's say, 9 to 8, that becomes almost impossible to start.
Right.
Right. And once we start at 16, 16 8, these kinds of rate, not 16 8. 16:9, I think it was. When we start getting into the more complex ratios, it starts to become more and more difficult. Number one, we can't do it with our fingers necessarily, but we can hear it. But then it starts to get so far that even our eardrums can't do it, and we
Right.
can't hear these notes that are so far away, and we have to modulate if we want to start getting to some of those other notes.
Right.
With the help of equal temperament. Okay, so there's number 5. Does that answer at all what you're talking about, Art?
I think so. Yeah.
Tom?
I have a comment about that. I guess in the barbershop world, people are very interested in just tuning because we're trying to reinforce overtones and hear those overtones when we sing. So
Mhm.
if you get the intervals perfectly lined up in low prime ratios, then those overtones really pop out and you can hear them.
Mhm.
But people seem a lot more confused about how you deal with melody in that framework and whether you sing the melody in equal temperament or you somehow adapt just tuning to singing the melody too. And I think that's an interesting question, and I'd like to know how to resolve that.
That's fantastic. So Tom is saying in the barbershop world, if you couldn't hear him, that they're working on always trying to tune up in a just way to low prime ratios so that they
Hmm.
can hear the overtones popping out on the top, and you get that famous barbershop ring on these chords, right? But how do you fit melody into that? So that's kind of part of what we were just talking about too. Do you sing the melody in equal temperament, or do you sing the melody in a just way? And that's the difficulty that Tom needs to resolve in his mind, right?
Well, assuming that it's all a cappella, then I would think you would have to sing the melody in a just way as well.
Yeah,
Right.
and so look at what we did on the board last week. We had
Right.
2 laws. We sang it without saying we had to adjust it. Everybody adjusted
You're right.
depending on the context. So
Right.
the melody in a 7-note major scale is not really a 7-note major scale.
Uh-huh.
There's 7 letters, but there's many more notes than those 7 letters.
Yes.
And I think
Depending on the context, right?
depending on the context, I think we as in-tune singers, when we're searching for those ringing resonances and the overtones, we're adjusting to find it. And the theory of the book is that you're adjusting to major thirds and perfect fifths because those are the low prime ratios, and that's what we hone in on and search for.
Well,
Uh-huh.
barbershoppers, the theory in barbershop is that the lead singer sings the melody, everybody tunes to the lead singer. But the question is, what does the lead singer tune to?
Mm-hmm. Could you hear
Right.
that?
Yes. Yes.
Yeah. It's, I think the answer that we come up with is that the lead singer sings the melody so it sounds pleasing, but I'm not sure what what that means.
Yeah.
Wouldn't it be logical to just like bring some kind of a pitch instrument and just, if it's in the key of C, then just blow C and just let it go after that. Kind of thing. You know what I mean?
And that's what they do, he says.
Right.
You just let it go after that. Well, and I suspect that different lead singers do it differently.
Hmm.
I don't know that, but if you listen to a really good vocalist and they sing a melody, you say, yeah, they sang that melody in perfect tune. But I'm not sure what that means in terms of just or equal temperament tuning.
Yeah.
Right. Right.
And
The only way you know is probably when you juxtapose that lead singer to a I don't know, either a just intonation piano instrument or a equal temperament piano, then you'll know, oh, okay, he or she is going to the equal temperament or the just. Because
right?
but if there's no reference, you probably won't ever know. Or something.
And might I suggest that when you say barbershoppers tuned to the lead singer, maybe that's in the general sense, but for the fine tuning, for the really going for those rings, to listen to that ringing resonance and the overtone screaming on the top, you're making more adjustments that they're not aware of.
Oh, I suspect you're probably right. And as I say, this is the theory.
Mm-hmm.
And I'm sure that the theory doesn't always get applied in practice. And it may not even be right, but that's the theory.
Yeah. So when we talk about tuning, okay, I want to tune to the in choir we say that we're tuning to the basses because the basses have the fundamental, which makes a lot of sense overtonally.
Right.
That's a general thing. If you're out of tune, tune to the basses. Okay. But once you're in tune, how in tune are you?
Right.
And what are you tuning to? So at that point, are
Yes.
you tuning a just third, or are you tuning an equal tempered third, et cetera?
Right.
Right. So
Right.
there's layers and levels of being in tune.
Right.
And
Right. Right.
so the deeper layers are saying, okay, we're tuning to each other. We're not just tuning to one line in any given moment. In any given moment, there are going
Yes.
to be discrepancies, as you'll see when we get into the lattice and we draw the lattice, which probably won't be till next week. And when we start looking at that, there's discrepancies that are specific in every key. For example, in the key of C, the two Ds, very, two very different Ds that are not even the equal tempered D. So there's at least three choices for D. And if you're the one singing the D in that chord, in that G major chord, then when it's your turn to adjust, maybe the sopranos have the D that time, but maybe the next time it comes through, the tenors have it. Now the tenors have to do the adjusting, and everybody has to do adjusting depending on the context and where it is in the music.
Well, or maybe if you're singing a D and you're singing the melody, you leave D in the same place. And when a different chord comes along and you're still singing D, everybody has to adjust you. But if you're singing D in the harmony and the chord changes and you're still on a D, you have to adjust to the new melody note. I'm not sure, but that seems like a reasonable.
That seems reasonable. It seems to me that that would pull a home tone out of whack.
Mhm.
And so now you're not in the same key anymore. You're a quarter tone sharp or a quarter tone flat.
Yeah, yeah, but
Right.
if the lead singer does it consistently
Mhm.
and stays where it stays in the same key all the way through, then you end up back where you started somehow.
Uh-huh.
And yeah, thing that I want to resolve because it's really difficult to think about,
Mhm.
but we do it somehow.
Yeah, we do it somehow, and groups that don't know anything about this theory and about the overtone series sing beautifully in tune.
Right.
Somehow they've figured it out and they're doing it, and it sounds terrific.
Right.
Yeah.
Right.
So excellent discussion.
Yeah.
All right, let's keep looking at some terms here. So number 3, we talked about this last week. So since perfect fifths, as legend goes, were given to us by Pythagoras, who discovered it and measured it on his monochord, we call harmony that moves in perfect fifths, we're going to call it Pythagorean. We'll talk about Pythagorean spines of notes, and we'll get to that later when we start talking about the lattice. And then harmony that moves by major thirds is called pentamerous. Good friend of mine was giving a talk about some of this stuff that she had gleaned from it herself, and she was saying that perfect fifths were pentamerous. And I had to go to her afterwards and say, it's you've got it the other way around. She goes, well, I was just giving one talk and there you have it. But it was not accurate because you think pentamerous 5 means perfect fifth. And
Right.
unless you know your overtone series and you know that the fifth partial is a major third, then you got to realize that fifths are thirds and thirds are fifths, right? And someday I'm going to make a t-shirt that says that 3 equals 5 and 5 equals 3. And you'll all be invited to buy one. Okay. All right. So Pythagorean, named for Pythagoras, are music by perfect fifths. We get that kind of music. Right, what did I play? I played 1 to 4 to 1 to 5 to 1. So we know that. Our ear understands that. It is so clear in our minds that we are just going, because we're going by perfect fifths. And when we go by perfect fifths, up or down, that's Pythagorean, and that the ear gets real fast because the low prime ratios are easiest to understand. Once we start getting to major thirds and we start moving this way, there's a lot more juicy harmony in there when we're moving by major thirds, and our ears don't get it as fast. And so when composers are doing modulations like that, um, they're going to be more careful about how they get from one to the other, because they realize that the ear needs some time to adjust to move by major third. That pentamerous harmony is really beautiful and really juicy, and really it has to be handled with care. But this has been going on since Beethoven. So, there's some wonderful pieces that I've looked at where he does that. He's in the key of C and then he moves down to the key of A flat and he modulates from one to the other, and it's a wonderful move. Um, but it's not as quickly got by our ear, pentamerous music. Okay. All right, going on. Number 4, in equal temperament, each half step is divided for convenience of measurement into 100 cents. If we divided a 19-tone octave into cents, the cents would be smaller because we've got more. Don't even, you can call them half steps if you want to. They don't have to be half steps, so you can name them whatever you want to name them. But we're dividing the octave, the 2-to-1 ratio, into smaller parts. Therefore, the cents will be smaller too. If you call them cents. And I don't know that any system actually does call them cents if you're in something other than 12-tone equal temperament. So for convenience of measurement, a half step is 100 cents. A whole step then is 200 cents. The major third that we're going to deal with a lot is 400 cents. Major third, 400 cents. A perfect fifth is 7 half steps, so it's 700 cents. And an octave is 12 half steps, so an octave will be 1,200 cents. Now, when we're talking about something like the 2 E's that we sing, and I tell you that the piano's equal tempered E is 400 cents, how many cents do you think the just E is off from that 400? Have we talked about that?
Yeah, you said it was 387 last week.
Yeah, I think it's 386 is what it is. So you're talking about 386 to 400. Which one? Can you hear that difference? Well, let's see. 386. That's only about what is it? 14 cents difference.
Mm-hmm.
So it's a very small difference, but we can hear it. We can feel it. We've sensed it. We've talked about it already, that we can tell that there's a difference there, right? And some conductors want you to sing it higher and some want you to sing it lower. And that's a difference of 14 cents out of 400. The perfect fifth is only off by about 2 cents. 2 cents out of 700, so that's like 702 cents, I think, goes the other way. 702 to 700 of the equal tempered. So perfect fifths on the piano in general are pretty good,
Right.
but they're not perfect. They're not as perfect as we like to think of them.
Right.
You can use them because when I have my kids sing every day, we start warm-ups, we always start with a drone. And then I sing solfege to them over the drone, but I don't play the notes on the piano so much, because if I do, they're hearing the equal temper tunings, but I want them singing the just tunings. So if I want them singing the just tunings, I'm not going to play them on the piano, certainly not the major third.
Right.
I'll sing it myself, right? And let them copy me. Okay, any questions? We're 1 through 5 already. Making good headway here.
Yeah, so that makes sense a lot, because when I tune pianos, the I have to adhere to a certain tempo of the beatings if you compare two notes together. So a perfect fifth is not exactly, so you tune to a very flat, no beats at all, which is not the way you're supposed to. It's slightly like a perfect fifth should be like, I believe is over sharp, like you said, a couple of cents. And that creates a beating of a very slow tempo, almost wavy kind of thing, right? Compared to the major third, which is, I have to beat it like, I believe it was 90 beats per minute or something like that. The beating should be a certain tempo. And again, if you're doing just intonation compared to that certain major third, it should be no beats for pure, tuning. But because of equal temperament, if you compare the major third, there's like a kind of beat, and it's not. When you tune a guitar, you're listening for no beats at all, right?
Yeah.
But on the piano, there's a major third, specifically the F4 and the the F3 and the A3. There's a certain exact beating that you do so that you're quote unquote correct on the equal temperament scale.
Wow.
Yeah.
I'm going to want you to come in here and demonstrate that for me on a piano. We'll pick one of my pianos and let you show us that art. That would be very
Sure.
valuable, I think, because I've
Yeah.
heard about this. I know what the beats sound like, but I've never really delved into it deeply for piano tuning. And
Uh-huh.
that's very relevant to what we're talking about here.
Yes, because you're doing it's basically relative tuning. You're comparing one starting note, which is tuned to, A440, for example, concert pitch, and you're actually using the overtone series to tune the rest of the piano. you know that's basically it, depending on what octave you are, of course. But the middle octave is what we call the temperament octave, and everything is tuned to that middle octave.
So you get that octave in tune first,
Yes.
and then you go out by octaves or
Yes.
from those
Yes.
notes?
From those notes, so you go up the high treble and then the bass. And of course there's some stretching involved and stuff like that. But the temperament octave is really, if it's done correctly, your ear should be really in tune to the little beatings.
Yeah.
Very interesting.
Tuned to piano? No. All right, bring your tools next week, Art. We're going to want to
Sure.
see some of this in action, right?
Sure.
That's awesome. Okay.
And it confirms what you said about 386, and then the perfect fix is just 702. So it's like, oh, that makes sense.
Yeah.
Totally.
And if you look in the back, of the book, there's a glossary of singable tones.
Uh-huh.
Let's see. You have your book, Tom?
No,
Come peek at mine here. Here's a glossary of singable tones in just intonation. So every time you see a dotted line, you're looking at the half step and how many cents it is. Then you look at all the other kinds of those tones and that you can tune to or sing to. And there's a lot of notes in an octave, isn't it?
Interesting.
Yeah.
Very interesting. Yes.
And like none of them line up.
Yes.
Overtone series, none of the ratios line up with the 100-cent half steps.
Yes.
Yeah, that's pretty cool.
And it's because, is it because of our ears, or is it because of the way the ratios are multiplied instead of additional, stuff like that?
I'm not sure your question.
Why doesn't it line up?
Because equal temperament for convenience has equalized everything into
Got it. Okay.
100
So,
cent half steps.
right.
That is
Right.
not overtonal tuning.
Right. So meaning the overtonal is not that linear, right? Just for clarity. I think I know the answer, but to sum it up, the just intonation is not exactly perfectly mathematically, coherent, shall we say.
Right. I think you're on to the right thing there. I'm just not sure how to say it correctly.
Okay. Okay.
But that's the whole reason we have equal temperament, so that if everything is equal, we can play in every key.
Yes.
If we were tuned to the overtone series, we would have to choose an overtone series to tune our piano to, and then it would work in one or two or three keys max, and then the other ones would start sounding wrong because the proportions would all be off.
Yes. Yes.
Yeah.
That's interesting.
Fantastic. That glossary of singable tones is on page 530 if you are looking at it. And these are singable tones, which means we can find those notes.
Yeah.
We can actually sing them and identify them. That's a lot of notes.
Yes.
To a single 12-note octave. All right, let's keep going. Number 6. Okay, so when an octave's frequency is doubled, we talked about last week when we sang Three Blind Mice or whatever it was, we were singing, and as the higher voices in the room and the lower voices in the room were singing together, we were actually singing in octaves, right? The same thing happens when you sing with your children and you're both singing together. The adult voice is higher, the adult male voice is higher, child's voice is an octave lower, so you're hearing the music in octaves. So if you take a frequency and you double it, you expand to the next octave, right? And then the next, and then the next. So the piano has about 8 octaves of C on it, and each of those is a doubling. Let's just say the first one would be 100. It's low C, which it's not. I don't know what the exact frequency is. Double it, 200, 400, 800, what did I say? 800, 1600, sorry, 3200. So it just keeps doubling and doubling, right? As we start getting way up there. And we can hear certain pitches. Did I say that right? 200, yeah, I did, right? Okay.
Yeah.
That's one thing. Octave expansion. If the first note is 3, then the next note is 6, the next note is 12. And if the first note is 5, then the next note is 10, and the next note is 20 and 40, etc. To make intervals easier to hear and work with, you want to get rid of all those lower octaves. So let's think about the ratio of 3 to 1 right now, which we said was a perfect fifth. From a C to the next overtone is C. That's a 2 to 1 ratio. Then the next one up is the G. It's an octave and a fifth away. Let me go ahead and draw this. All right, so let's remember our overtone series. And if we start on this low C, which is our first note, the next overtone up is going to be this C, right? That's a 2 to 1 ratio with the first one. 2 of these for one of these. 2 vibrations here, 1 vibration here. When we get up to the next note in the overtone series, which we played at the piano last week, we've got a G. That's at a 3 to 1 ratio with this one. We divide our string into 3 equal parts. We hear the perfect fifth. The next one is going to be another octave C. If this is 1, this is 2, double 2, you get the fourth partial, 2 to 4. That makes our 4 to 1 ratio with this one. Okay. Next would be our E. That's a 5-to-1 ratio. 1, 2, 3, 4, fifth partial, 5-to-1 ratio. Next would be another G. And this was the overtone chord that we played out of the first 6 partials. This C and then these ones. Now notice if this is one, let's call it a 1-to-1. This would be a 2-to-1. This is a 3-to-1. This is a doubling of that one, so this is 4-to-1, comparing that one to this one. This is our 5-to-1. What is that one?
That's a doubling of the 3-to-1.
Correct.
Yeah.
It said it. It was 6-to-1. So every G is going to be a doubling of that 3, right? The next G up will be the 12th partial. The next octave up will be the 8th partial, right? And so we can just keep going. So let's see, the next one would have been B flat, which is our 7th partial, which the next one would be our C, which is our 8-to-1. Now, when we deal with music, we don't deal with this wide of a range of notes when we're talking, say, about a melody. So what's the best way to do this? We need to get everything within an octave. So if I tell you that I want to know what the ratio is of a perfect fifth, well, here's the perfect fifth from this low C to this G. What do I want to do? I want to get rid of this octave here. Because if I'm going to be dealing with this to this, that's too far apart. A 12th. I want to deal with 12th. Or if it was this C, then the next note would be, note would be way up there. That's too far. So I want to get my notes within an octave to deal with them for convenience and to see them and hear them and work with them better. So I'm going to get rid of this octave. How do I get rid of that octave? I've got to change the ratio of this note. It's not going to be 3-to-1. This is where I'm testing my ability to explain this stuff. It's clear. I don't know if it's clear the way I'm going to say it. So tell me if you're confused.
I could see the potential of mistakes and stuff. So yeah, I don't blame you.
Right, okay. Okay, this is a 3-to-1. 3 of these vibrations for 1 of these vibrations of these notes. Let's just get rid of some of this extra stuff. Okay, this represents my fundamental note, my C, right? Everybody say yes.
Yeah.
Yes.
This represents my perfect fifth, right? Or my 12th.
Yep.
Okay,
Yeah.
let's change this note to move it up an octave. How do I change that 1 to go up an octave?
Double.
I double it because
Yeah.
octaves, to expand them, you double them, right? So now I'm going to call it a 3-to-2. And it's going to mean the same thing, except they're not going to be out here. They're going to be over here. Does that make sense?
Right.
So the ratio of a perfect fifth is not 3-to-1. 3-to-1 is the ratio of the perfect 12th.
Right.
The perfect fifth is 3-to-2. And that's how we get the actual location of that note that is within an octave of C.
Got it.
Make sense?
Yeah. Well,
Yes.
you've also got it in the bass clef there. You've got a 2-to-1 C and a 3-to-1 G.
Right.
And so,
I'm taking this guy and putting him next to this guy.
yeah.
And so we get our 3-to-2, right?
Yes.
So I get rid of this low C and now I'm in there. Make sense?
So it's 3-to-1 compared to the low C. That's the
Correct.
difference. Yes.
Correct.
Like you said, the 12th. Yeah.
Well,
Right.
to deal with 12s, that's only the perfect fifth. Now we got to add a whole bunch of other notes as we're studying harmony. And we're going to be using ratios that are that far apart. It doesn't make sense. So we got to put
Right.
them close together to be able to work with them. Now
Yes.
let's do that exact same process with the fifth partial. Here's C, here's the next C, here's G, here's our C, here's our E. At a 5-to-1 ratio, whoops, not 51, 5-to-1 ratio with this C. How do I get rid of all the extra octaves? Because now it's 2 octaves and a third. That's too far away. What do I do?
You double the octave and then add, yeah.
And which one's the octave?
Yeah,
Say it
the
again.
ratio should be at least 2. The second number should be 2.
If we change the second number to a 2, we're essentially getting rid of that octave.
Right,
But I'm still too far away.
right.
So what do I do next?
Get rid of another octave.
Get rid of another octave. How do I do that?
Right.
You double the.
Double it again.
Yeah, double
To
the
4.
to a 4. And now we got rid of that one. So we are now octave reducing by taking away the lowest octave and now getting the notes to be sitting between this C and this E. The ratio of a C to an E, which is a major third higher, is a 5-to-4 ratio. For every 5 vibrations here, you got 4 vibrations here. Does that make sense?
Yes.
It's a whole new thing. It's a whole new way of looking at things. But if you can get the idea of harmonic, of octave reduction, getting rid of the lowest octaves so the notes are closer together, they become a lot easier to work with. Octave expansion
Right.
just means I'm adding octaves by doubling. But now I can take some away to octave reduce to get the notes closer together.
There should be an equation for that you could plug in something. It would make sense to me that there would be some kind of formula, an equation that you could just plug in the numbers and thus produce that kind of ratio.
And there kind of will be when we look at the lattice next week. It's going to be this idea of multiplying. When I say harmony is multiplicative, you're going to see it on the map. And you're going to say, oh, okay, if I multiply by 3 and then by 3 again, I get 9. And now I'm 2 perfect fifths. So
got it.
That's going to start to make sense as
If you talk about frequencies, then there is a formula. You say, okay, take the fundamental frequency, multiply it by 5, and you get the E, and multiply it by 4, and you get the C. The frequencies of those 2 notes, so that they have a ratio of 5-to-4.
Right. Right. So Tom's giving us, if you couldn't hear him, he's giving us the idea that you take the frequency and then you multiply it by 5 if you want to get a major third, or you multiply it by 3. Then it all comes down to when I first asked you guys, can you multiply by 3 and by 2 and by 5?
Yes.
And if you can, you're going to be okay with this learning all this stuff.
Right.
That's what it's all about. Those low prime numbers from the overtone series that help our ear to understand harmony. And it's not just these, it's the compounds of these.
Yes.
Multiplying, 2/5 over is times 3 twice.
Right.
Multiplying by 5 means you're moving 2 major thirds away. So we'll get more and more to that.
Right.
So just look at number 6 again. When octave's frequency is doubled, the next octave higher is produced. This is called octave expansion. 1 becomes 2, then 4, then 8, then 16. 3 becomes 6, then 12, etc. 5 becomes 10, then 20, etc. To make intervals easier to hear and work with, we remove lower octaves from compound intervals in a process called octave reduction. Take away the lowest octaves to get them between in a single octave, right? The ratio has to be between a 1 and 2. Okay, so examples from the overtone series. The 12th becomes a 5th instead. We're used to doing this anyway. We did this in music theory when we were harmonizing and saying, okay, these notes are a 5th. Really, they were a 12th. And these notes between the bass and the alto are a 5th, which was really a 12th. That was parallel 5ths. Even though they were parallel 12ths, we were calling them parallel 5ths, right? So we've done that in our training before. 2 octaves in a major third simply become a major third. We're just getting rid of the lower octaves, and that's called octave reduction. Okay, chew on that for a while. Let's go on to the next page. Number 7, the scale degrees 1, 2, 3, 4, 5, 6, 7, 1 in solfege are called do, re, mi, fa, sol, la, ti, do. And in sargam, they're called sa, re, ga, ma, pa, da, ni, sa. Now, I put this in there because Aladdin uses this a lot. He likes these syllables better because they're more open vowels. If you notice, most of them are ahs, not all of them. And so they allow you to really open the mouth and sing sa, re, ga, ma, pa, da, ni, sa. And the other beautiful thing about these is there are no different syllables for chromatic notes. So whatever of the saws, well, you sing saw and that would stay the same. Pa is going to be your 5th. Ma is going to be your subdominant. And then whatever ray you're going to sing, you can sing it a little higher or a little bit lower, depending. They're going to have different ratios if you're not singing it in equal temperament. And even if you are, you can call it ray, but there's too many variations. So since there are so many variations of ray that we can sing and tune to, um, we're not going to have a different syllable for each one. So ray and ray flat or raw um, is going to just be ray in sargam. So you only get 7 syllables for sargam. You don't have like the 12 chromatic do, di, re, re, mi, fa, fi, sol, si. You don't get that. And I like it because it helps your ear to know exactly where you're at. Sa re ga ga ga, sa re ga ga ga, sa re ga, ma ga re sa, ma ga, pa ga re sa ni sa. And you can slide in and out of notes a lot easier. Solfege is you have 12 destinations. It's equal tempered, is what we use to learn our equal temperament. And solfege is good, and I use solfege all the time. Sa re ga is good for other reasons, and he uses it a lot in the book. So I just want you to be aware. Look at the notes. Number 3 is ga. So when we're talking about major thirds, he's talking about ga-blooded music, he calls it. When you're talking about pa, you're talking about pa-blooded music, or music that moves by perfect fifth, harmony that moves by perfect fifth. So he refers to that a lot in the book. I thought I would put it in there on this sheet for you. So here's the relative terminology. Perfect.
I wanted to say something about that.
Oh, go right ahead, Tom. Sorry.
When you're singing harmony, it's much easier to tune when you're singing the same vowel and matching the vowel, because non-matching vowels can really get in the way of tuning.
Yes, non-matching vowels can get in the way of your tuning. Absolutely. So having most of them as ah, sa, ga, pa, sure.
Yeah, especially the root 35th.
Yeah, and ma, da, pa, not ma, da, sa, pa, ni, re. That one's going to be off, right? But the subdominant certainly and the dominant chords are going to be easier to sing when you're singing with other people because you can line them up that way with the same vowel. Yeah, it's nice. And he jokes about it in the book. He says it's kind of like learning, what did he say? Like learning astrophysics in Turkish. You're learning 2 systems at once. He says, but in this case, it's valuable if you learn a little Sargam and learn to sing your lines in Sargam instead of singing them in solfege. But if you want to use solfege, use solfege. Just know that he's going to use this terminology a lot. And that does come from his studies for 20 years with Pandit Pranath, who taught him raga. And that had a lot to do with how his understanding of this theory has come about. Okay. All right. So relative terminology. Perfect fifths are Pythagorean. They are third partials, and they are pa or pa-blooded. Major thirds are pentamerous, threes or fives. Fifth partials, and they're ga or ga-blooded. Overtonal music is north and east on the lattice, but we haven't got to the lattice yet. And reciprocal is south and west on the lattice. We'll talk about that later. Overtonal is dominant energy, and reciprocal is subdominant energy. Reciprocal, hold that word in your pocket. We'll get to that very soon, as early as next week. Now, last week, what I had on the board here with the two different A's, we were actually singing differences in pitch with the two different A's. And we'll do a little bit of this more before we leave here. But the two different A's, when we hold the note and our tuning changes depending on the context of the notes around it, the difference between the two notes is called a comma. A comma is a small interval between two tones near in pitch, but different in the way the harmony generates them. And that'll make more sense as we get more into these ratios and stuff like that. Okay, so the comma and singing through the comma, it's a big deal. And understanding it as a musician is a big deal. We did it last week. You've already sung through a comma. So we sang through the two sixth scale degrees, two different ones depending on the context. And we all had a description of what it felt like to us. And some of us maybe said up or down. Some said it felt like it locked in. Some said different things. We all had a different experience of it, but we all did it and we all felt the difference. So when you're feeling that difference, you're going through the comma and the energy of that note changes. And the tuning actually changes. The pitch frequency actually changes. And when we hear it played on an equal tempered piano, we still sense it because somewhere in our bodies, we still know those just resonances, just like we still know the cycles of night and day, even though the light bulb has kind of dulled that a little bit, right? We can still sense it. And in this case, we can still sense it too. One last story I'll share with you. I wanted to get on record as saying it. So if you saw my Facebook post the other night, I was with Bruce Crocker's telescope in my backyard, and we trained it on Saturn, and we saw the rings of Saturn. It was fantastic. My son and I were up at 2:30 in the morning and we're looking at things. We went and woke up my wife, come out and see the rings of Saturn. And so we were so excited that we could see them from our backyard. And then we turned it on Jupiter, which was much brighter in the sky. And as we turned it on Jupiter, we could see Jupiter's moons. And I was like, holy cow, I can see the moons of Jupiter. Now, Jupiter has about 79 moons. I think exactly 79 moons. And of those, 4 of them can be seen pretty clearly from your backyard with even binoculars. I think you can find them. So we've got a 6-inch telescope we're looking through that we had borrowed. And so we're looking at them and you could see 3 of them very clearly. And I think they were Io, which is the closest to Jupiter, and then Europa. Do you know these? And then Ganymede, and I don't know if we could see Callisto or not. So those are the 4 Galilean moons, because Galileo saw them. He was one of the first people to see them. And it was the first time that we realized as a human race that we were not the only center of the universe. The universe didn't just revolve around us. Other things revolved around other things out in the heavens. And it was a huge deal. So we're looking at 3 of these moons. Well, after I got down off the high of looking at the moons from my backyard, and put everything away, and I went to bed and I took out my phone and I was researching some more on the moons of Jupiter. And it turns out that those Galilean moons, I thought this was fascinating. I'm still fascinated by it. All right, so here's Jupiter. And then you have, well, let's make it bigger. Here's Jupiter. And here's the closest moon, which is Io. Let me put it up here. And Io is going around Jupiter. Let's call it at a 1-to-1 proportion, right? The next moon, if I'm not mistaken, is Europa. And what proportion do you think Europa is in?
I'm guessing 2-to-1.
It's moving at a 2-to-1 ratio with Io. Every time Io goes around once, Europa goes around twice. That's an octave, right? The next one is Ganymede, I believe. Terrible circles. And what proportion do you think Ganymede is in?
You're really surprised that it's not 3-to-1.
It was 4-to-1. It was the next octave. It was the next doubling. So it takes 4 times for this to go around as this goes around once around Jupiter. So you've got octaves going on around Jupiter. I thought that was just astounding and amazing, and I loved it. The ratios break down later after that, but those 3 of them are in those stunning proportions, and I thought that was pretty cool. So there you have it. Came at a very timely time. And if any of you ever want to come and see these, come to my backyard at 2:30 in the summer, and I'm happy to host you.
Ring the doorbell.
Ring the doorbell or tell me ahead of time that you come in, and we'll go in the backyard and set up and we'll go look at these things. It's pretty awesome. All right. Any more questions, anybody? Okay, there's the terminology. There's where we're going. Next week, we're going to create a lattice of thirds and fifths, and we're going to see how everything compounds and what reciprocals are and how that works in our studying of harmony. Okay, and I'm going to stop the recording now. Art is now driving. Okay, I don't recommend necessarily trying to find harmonic experience while you're moving in the vehicle. But we might do some little experiments here. Okay, everybody, you have a great week. Listen to this several times if you have to. Make sure you understand all that terminology, or at least are starting to let it sink in, and we'll continue on from there next week. All right, bye.